Well, hey there, this is Mrs. Sharp, and I'm going to start to go over Learning Target 4.2 with you just because if you're watching this video, I am not quite sure if I will be back with you tomorrow or not. So if I am, we'll do this in class tomorrow, but if I'm not, I'm hoping you'll do it in class individually and that you'll still get the information that you need. So just as a reminder here, I'm trying in your Unit 4 to indicate to you where your information can be found in the book for a learning target. So this will be found in section 5.2. It is Learning Target 4.2. And in this we're going to use what's known as Bohr's model of the atom to show how electrons are spaced in energy levels at definite distances from the nucleus. We're going to describe the relationship between an electron's distance from the nucleus and its relative energy or stability. And we're going to describe what happens when electrons move from one energy level to another in an atom. So those are our three goals for 4.2. Alright, so let's take a look at the Bohr's model. And the Bohr model is based on the work of Niels Bohr, 1913. Remember, he's coming off of Rutherford's model. And in Rutherford's model, I'm just going to do a quick sketch here. In Rutherford's model, you had a teeny tiny nucleus with lots of empty space, but the electrons were just sort of thought of as randomly spaced around in the electron cloud. They weren't organized at all. We really didn't learn about them at all, other than the fact that they existed from Dalton to Thomson to Rutherford. We just knew they were there, and by the time Rutherford came along, we knew there was a nucleus, and the rest of it was mostly empty space, and in that empty space is where the electrons were. So Bohr came along and sought to get some more information about those electrons. And here's what he came up with. This is kind of his quote. He said, the electrons in the atom move at a fixed distance from the nucleus, and these are called energy levels. So that fixed distance from the nucleus was the important thing, and he made an analogy to planets moving around the sun. So he pictured it as that fixed distance was like a fixed radius with the sun at the center and the planet in its orbit. The electron would be at a fixed distance or radius from the nucleus. And then he went on to also say, very important here, each energy level has a certain amount of energy, and we're going to add to that increases as electrons move further or move away from the nucleus. So in other words, the electrons with the lowest energy would be those electrons in the energy levels closest to the nucleus. So that was the Bohr model. So taking those electrons that were kind of randomly dispersed in that empty space and organizing them in these energy levels, which are at fixed distances from the nucleus. Believe it or not, this information came from the equations that we have been talking about. So the speed of light equaling wavelength times frequency, and the energy of a photon equaling Planck's constant times frequency. Bohr used that information to come up with this model. And we're going to explore that a little bit more here. Okay, so if we picture Bohr's model now, we can picture, again, a teeny tiny positively charged nucleus, and in the first energy level here, we would draw it as a ring. You may have learned that this is called an orbit. You might have learned that it's called a shell. We're going to call it an energy level. So in the first energy level here, first energy level, Bohr pictured those electrons moving at that fixed distance from the nucleus, and this would be our lowest in energy. You guys may or may not remember that later on we figured out exactly how many electrons could be held in that first energy level, and that was 2 electrons max. Then he pictured additional energy levels being tacked onto that, so this might be our second energy level. and the second energy level would have a little more energy than the first energy level. And again, that's because those electrons want to be as close to the nucleus as possible. They're oppositely attracted. And so being in the second energy level would not be preferred. Being in the first energy level would be preferred because electrons are lazy and they like to have low energy, and they have low energy when they're close to the nucleus. And that second energy level, you might remember, could hold 8 electrons max. And we could tack on a third, a fourth, a fifth, a sixth, a seventh. It turns out we haven't discovered anything beyond a 7th energy level, so that's as far as we've gone so far, but theoretically you could have as many energy levels as you needed to have for how many electrons you have. So that's the basics of Bohr's model, and now I want you to create kind of a little column here where we have the energy level, the max number of electrons, and the amount of energy. So the energy level 1 has a max number of electrons of 2, and its energy is lowest. Energy level of 2 has a max number of electrons of 8, and it's a little bit higher. Energy level of 3 has a max number of electrons of 18. Its energy would be a little bit higher because it's farther away. Energy level 4 would have a max number of electrons of 32, and it would increase in energy. And the reason I show you this chart is because students do really well remembering like the 2 and the 8 electrons for the first and second energy level, but they kind of break down when they get past that. And so I'm just going to tell you guys, and this is really the most important line of this whole little chart, and that is whatever energy level you have, let's call it N, and N could be any number, N could be the 6th energy level, the max number of electrons is equal to 2N squared. So whatever energy level you're talking about, if you square that energy level's number and you multiply it by 2, you are going to get the number of electrons that can be held. So let's try that with 4. 4 squared is 16 times 2 would be 32. So you never have to memorize this 2, 8, 18, 32 business again. You can just instead remember that any energy level, if you square it and multiply it by 2, that's going to tell you the maximum number of electrons. Now remember, that's maximum. That doesn't mean there has to be that many electrons. That just means they can go there. There's that many that can be held there. So for example, if I had 3 electrons, I would need to put 2 in the first energy level and then only 1 in the second. So they would prefer to go in order of lowest to highest energy.